Hey, welcome back. In this video, we're going to talk about confidence intervals for population proportions. You've heard of these confidence intervals probably many times in your life. For instance, if you've heard a statement something like 35% of the population likes Hawaiian pizza, plus or minus 3%. That plus or minus 3% is discussing a margin of error around the 35% proportion that has been described. Importantly, when we're describing confidence intervals for population proportions, we're looking at binomial distributions. Previously, we've talked about those as success and failures, or yes and no. In these cases, it doesn't make sense to talk about the mean or average of a population. What we're looking at is the proportion of a population that favors something or dislikes something. Again, any situation, we have a binary choice between two things. As with many things in statistics, the description might seem a little bit overwhelming, but as you'll see in the example that we'll do in a second, it's actually pretty straightforward. What we'll do is just create this basis, this proportion, which we call a point estimate for the true proportion of the population. And then we just need to find an error bound, that's that plus or minus 3%, to create our confidence interval. All right, so let's get the details out of the way. So we define X to be a random variable for the number of successes in N trials. And again, this is a binomial distribution of successes or failures. For P, the true population proportion, which we probably don't know, we're sampling to try to get an idea of this interval through which our true population will lie. What we'll do is we're going to define a point estimate, which is just the number of successes from our random variable divided by the number of trials. And then we'll define our error bound with this formula right here. Importantly, if our P, the true proportion of the population, is not near zero, and if our N is large enough, we can actually use a normal distribution to approximate the true proportion. Importantly here, in our analysis of the error bound, you'll see this z-score. Previously, for means, we had to use the student t-distribution or these t-scores to create the error bound, but we're going to go back to normal distributions and use z-scores. Before I jump into the example, I want to talk about this critical value, this z sub alpha divided by 2. We've talked about this a little bit, but I just want to address this directly right now. This is a z-score based on these confidence intervals. I'm going to talk about the 90%, 95, and 99% confidence intervals because those are the most common, but I'm also going to talk about if you were given or asked to find a 99.9 or 80% confidence interval, how would you go about finding this critical value in order to evaluate the error? Again, these critical values are simply z-scores, the same z-scores that we saw when we were first introduced to normal distributions. For instance, if we're looking at the 90% confidence interval, I have this beautiful normal distribution bell-shaped represented here. The 90% is that bit in the middle, and then we have these two tails. The first question is, well, how much do we have on each of these tails? Importantly, that's what we mean by this alpha. This alpha is the area or the proportion in these two tails combined. Well, we have 10% outside, and we know this is symmetrical. So we know that each of these has 5% of the population in them. And then for the 90% confidence interval, the z-score that we're going to use to calculate this error is the z-score that represents this place right here. We will call this z sub 0.05. This 0.05 is a one-tail description of this z-score, where this is the amount of the proportion of this population that is to the right or greater than this z-score. Though importantly, if you're going to use technology like a TI calculator, what you would type in is inverse norm or inv norm. And then here what you type in is not 90%, but you're going to type in the percentage less than that z-score. So in this case, it would be 90 plus the 5% or 95%. So that's just the details of this notation and why we're going to use 0.95 for a 90% confidence interval, but you don't have to go through this every single time. In fact, we are going to have known critical values for these three confidence intervals, and it's pretty straightforward. You think for the 95%, there's 5% left over, cut that in half, you have 2.5, add 2.5% to that, and you're going to get 97.5. So for this z-score, or this critical value, what you would type into a TI calculator, or Google Sheets has a very similar function that does this for you. In this case, it'd be 0.975. And then finally, you do the same math for the 99%, and what you'll get is 0.995. And even better than that, we won't have to calculate these every time for these three confidence intervals. In this case, we know that this critical value is 164. For the 95%, it's 196. And for the 99% confidence interval, it's 258. I just wanted to talk about this in this way so that if you're given a confidence interval that's not one of these threes, you know easily how to find that critical value. But I would write this down somewhere in my notes right away. For a 90% confidence interval, this is my critical value. For 95%, this is my critical value every time. And for 99%, this is my critical value, or in other words, the z-score I'm going to use to calculate this error bound. All right, that's enough of the setup and the theory. Let's get right into an example to make all of this seem a lot more simple in our minds. We have a survey that is conducted amongst 200 college students to find out if they prefer online to in-person classes. Out of the 200 students, 120 of them said that they prefer online classes. All right, so the first thing I'm going to do is to develop this point estimate for the true population, which is this P prime. I do want to say at this point right here that instead of P prime, you'll often see this P hat. Importantly, they mean the same things. They're just two types of notation for this point estimate. But if I'm going to find P prime here, what I'm going to take is my random variable for the number of successes and divide it by the number of trials. Well, this will simply be the 120 divided by 200. So P prime equals 120 divided by 200. And when I threw that in my calculator, I got that to be the proportion of 0.60. So this means that 60% of those that responded to the survey favor the in-person classes. And in fact, I use 2 decimal places here, but don't need it. I'm going to cut off that last 0 before I move forward. And importantly, in the work of creating these confidence intervals for these population proportions, the only nuance is the work of finding this critical value, or this z-score, for our confidence interval. As we previously discussed, for a 95% confidence interval, we'll use 1.96. And again, we could find any percent of confidence interval we would like here. All we would do is change this score. That is going to be this value right here in the error. Just quickly before I write it out, I just want to speak to the rest of this formula. It can look crazy, but it's not. I mean, really, this P prime is this point estimate, or the proportion of students who said they prefer online classes. The 1 minus the point estimate is simply the students who said they did not prefer online classes. So 1 minus P prime would be 0.4, would be the proportion in this case. And then we're dividing by n and taking the square root. But here's the work. To find our error, what we would do is take this critical value of 1.96, and then we're going to multiply that by the square root of 0.6 times 0.4. And again, these two values, based on this formula, sure as heck better add up to be 1, divided by our n. Our n in this case is the number sampled, which is 200. And when I threw that in my calculator, what I got was 0.0679. I'm telling you, it looks crazy, but it was really easy. That's all the work. All we need to do is define our confidence interval. In this case, what we're going to do is take this 60%, or 0.6, and we're going to subtract this error of 0.0679, comma, that's our lower bound for the interval. The upper bound will be 0.6 plus 0.0679. And when I threw that in my calculator, what I got was 0.5321, comma, 0.6679. So this is our 95% confidence interval for the proportion of students who prefer online classes. Importantly, how we would describe that is that we would say that we are 95% confident that the true proportion of the students who prefer online classes lies between we'll say in percentages, 53.21% and 66.79%. And finally, I just want to emphasize again, the only nuance to this process at all is finding this critical number, which is based on what confidence interval you're attacking. And again, these are known critical values or z-scores for the 90%, 95, and 99%. Write those down, keep those. Those make your life nice. And if you're given a strange confidence interval like 87% or something like that, it does not take much work using technology or a z-table to find the z value that you're looking for.